Assalamu alaikum, everybody. Good afternoon, and thank you very much for having me here today. As announced, I will be talking about the most basic part of radiology research, and it will be most related toward the use of gold nanoparticles and gold nanorods with the radiation therapy. So, if I ask you that what do you know about the nano world, so most of the students or we are aware of the nano world, the Legos that you build the Legos and you can build the house. But how we can make a use of nano world in biological application? Let's say what is what in this world. So nano world is very diverse. We have a lot of kind of nanomaterials. If we go by the names, we will have liposomes that can be used for the drug delivery. We do have dendrimers, hydrogels, and layer bipolar, mesopolar silica, gold shell, iron oxide shell. These are some of the kinds of nanoparticles that are used heavily in biology application. But most of my work is concentrated towards the platinum nanoparticles or gold nanoparticles. So if you go on the PubMed and you search, you will find that it's a quite old research that I have done, but a lot of research publications are still coming from for the application of nanoparticles in radiotherapy field. So if somebody is interested or want to work in the radiobiology research or nanoparticle research, the main thing that you should know that there are factors that the effect of nanoparticles can be dramatically changed based on the size. So the speaker before me, I think Yusuf, has talked about the high Z number of gold nanoparticles, and this is very much acceptable in the radiobiology field. That if you have a nanoparticle, especially gold with a high Z number, it can absorb the radiation energy and then it can emit that energy towards the cancer cell. But what results I will show you with the different size of nanoparticles, it's a bit contradictory to what literature said. Then we can do a lot of surface modification for the nanoparticles to make them targeted towards the cancer tissue. Then there are different shapes. So they are nanorods, they become cylindrical, there is star-shaped nanomaterials, and then of course we can change their hydrophobicity. This is just I'm pitching in, so the people who are not aware of the nanoparticle field, they can relate with my results. So how it started the whole journey. So this is a very classical paper that was published in 2007 by a group of Professor Kajita at University of Tokyo. And what they proposed for the first time is that platinum nanoparticles might have the SOD catalyzed mimetic activity. What does it mean that if the nanoparticles have a SOD catalyzed mimetic activity, so practically they can squash the reactive oxygen species. And all of us know that most of the effects of radiation are because of the free radical formation or the formation of reactive oxygen species. So they very efficiently propose that if you use platinum nanoparticle, which is a quite smaller size, that is 2 nanometer. So it can sequence the production of hydrogen peroxide and also sequence the production of superoxide. So we start collaborating with this group and take the nanoparticle and we want to try it with the radiation. So these are all the research products. So I would like to emphasize when we talk about radiation oncology, and most of your clinicians, so you basically focus on the radiation therapy. But in a radiological sciences department, you might have other physical modalities that can be used as an adjuvant for the radiotherapy. Let's say the lot of projects that I'm involved are based on radiation therapy, and it's also on ultrasound and hyperthermia, which Dr. Philip had yesterday. He briefly explained that we should add hyperthermia also in radiation therapy. And one of the newest innovative physical modality that is coming is called as cold atmospheric plasma. So this also can be used as an adjuvant for radiation therapy. So let's compare these physical modalities, keeping a radiation. So if you compare these physical modalities on the scale of pressure, time, and energy, so we can see clearly here that plasma chemistry or radiation chemistry, they have a difference between pressure, time, and energy. But what makes these physical modalities common? So there is one common factor which all of these physical modalities have, and by this factor they induce most of the cell death, especially in cancers. And this is the production of reactive oxygen species or redox signaling that they have in cancer cells. So let's talk about radiation. So if we see, radiation can induce most of the effect by its indirect effect by causing reactive oxygen species inside the cell and outside the cells. Ultrasound, which is mechanical kind of stress, it mostly induces cell death by inducing an intracellular loss beyond that when its intensity is increased beyond the cavitational threshold. Similarly, plasma, which is a kind of innovative physical modality, can use a abundant amount of reactive oxygen species outside the cells and less intercellularly. Hypothermia can only induce rust formation during heating, and it can also increase the membrane permeability of fluidity to have a great influx of blood. So these are the physical modalities. So based on their target and the downstream signaling, the cell will either go over the differentiation or they will go toward the cell death. So as of course, I cannot cover all of these physical modalities, but we have done a lot of work with ultrasound and other things. If you are interested, maybe we can discuss it more. But what we did initially, we took these platinum nanoparticles and we tried to combine it with different physical modalities, let's say with radiation. So what we found with the radiation, it was very surprising results that when we have a small size platinum nanoparticles, they actually squeeze your radiation-induced cell death. So that means they could have a radioprotective effect, but these nanoparticles cannot induce cell death in combination with radiation. Then we try to combine the same nanoparticles with hyperthermia and ultrasound, and we found that with the ultrasound they can enhance the cell death. So that was very interesting. To think of why nanoparticles are behaving differently when you have a different physical modality. So we come up with the idea, what about gold nanoparticles? Because gold nanoparticles are the most frequently used nanoparticles in case of radiotherapy, and we don't know what would happen. And the size we choose for our study is very small, that is 2 nanometer. These are the experiment protocols. We irradiate our cells and then we perform a lot of endpoint assays to check our hypothesis. So if you see this results, this is our first result. We compare size of gold nanoparticles at 2 nanometer, 40 nanometer, and 100 nanometer, and try to combine with at a dose of 10 gray. And you will see surprisingly here that 2 nanometer can suppress your cell death, while 40 and 100 does not have much effect on the radiation-induced cell death. So these just shows us that if the size of nanoparticles is small, so you can actually not helping the patient, and it actually is provide a mitigating effect towards radiation or radioprotection. So these are some of the underlying experiments we confirmed with a lot of experiments. Like you can see here that your apoptosis was completely inhibited in the presence of small size nanoparticles, and the DNA fragmentation was also protected. Loss of mitochondrial membrane potential, intracellular calcium was also protected by these gold nanorods. These are the Western blot, very classical Western blots. You can see the caspase 3, which is the main executioner of apoptosis, was completely inhibited in the presence of these gold nanoparticles. So the point I would like to make here, if you are planning to use nanoparticles as an enhancement agent, it is very important that you should choose a proper size and proper surface and shape. Otherwise, it could have a differential effect, and that our studies have proved that. So what we found that if we use nanoparticle with ultrasound, it can actually enhance the cancer cell death. But if we use it with X radiation, it actually uses the radioprotection. So this is something that is taken in consideration. Then I will just briefly talk about the nanorods. So now the world has been changed from gold nanoparticles towards the nanorods. So as the name suggests, nanorods are the long cylindrical shape-like structure, and they have a high aspect ratio. That means there's difference between length and width. And why we are interested in nanorods? Because nanorods are a very good theragnostic agents. For example, and the hypothetical idea is that if you put radiation with the nanorod, so basically nanorods are going to go inoculate more in cancer cells, and they are producing a heat. So these are kind of all the nano structure that we have. So if we have gold nanoparticles, we have nanorods, nanosphere. A lot of variety came in case of nanomaterials. So why nanorod is a good option to use with the radiation therapy? So most of you may be aware of the photothermal therapy. So nanorods were actually first used with the near infrared ray. So what they did they actually inoculate the nanorods into the tumor by injection, and then they put a near infrared ray. And this near infrared ray actually work as a heat generator in a tumor core, and because of this heat generation, they were able to see the cell death in the cancer tumor core. So getting this idea, it is reasonable that nanorod can be combined with the radiation therapy. And what we did it, because there is not much work has been done, because nanorod is a very new field, people are still popping in this field, and these nanorods can be synthesized, and you can even buy from a commercial sources. So just again, we need to take care of the different sizes. So what the one we use here is for 10 nanometer sizes. So the nanorod is also available from the size of 10 nanometer towards still 100 nanometer. So nanorods give us a very good result. So this is in case of Morpho cells. So you see we tried nanorods alone, and we try to combine with a very, very low dose of radiation, that is 2.5 gray at a basic research lab. And you can see here the combination of 0.5 nanorods in with the 2.5 gray can increase the number of your dead cells. Similarly, when we check at the DNA fragmentation level, then the percentage of DNA fragmentation was completely increased in the combination treatment. What interesting was that these nanorods can also able to induce a DNA damage response in combination with radiation. These are the fraction of cells. So you can see here about when we combine it with 0.1 dose, you can see about 30% of increase in cancer cell death. But if you combine at a 0.5 dose, you will see that about 65% of your cells are already going in apoptosis. This is a very exciting result to see. Then, as I said, one of the main mechanism for nanomaterials and radiation is the redox signaling. So you can check redox signaling right after you irradiate your cells, and you check via flow cytometry. So this is for the superoxide. So superoxide was increased in combination treatment, and then also the production of hydrogen peroxide was also increased in the combination treatment. One of the most important thing that happened when your antioxidants are going up, your antioxidant system is also going down. So we also confirmed that they're working in parallel. So when you have increased loss generation in combination treatment, your GSH system is also getting increased. Loss of GSH is also getting increased. And we confirmed that what kind of pathways can be involved in combination with nanorods and radiation. This is the expression of FAST, which is increased in case of combination treatment. That means your extrinsic pathway is also upregulated in the combination treatment with the activation of caspase 8, and then the downstream signaling towards the caspase 3 and BCL2 backs. So these all results actually conclude that nanorods and radiation combination not only induce your intrinsic pathway, but it also can incorporate your extrinsic pathway of cell death. So this is a summary that if you combine nanorods with X-rays or ionic radiation, what they do at first, they will actually work on a GSH level. They will try to inhibit the GSH in cells, and as a result of that, there will be a huge abundant amount of reactive oxygen separation, and then it will go to mitochondria and leads to mitochondrial membrane potential, and the downstream signaling was activated, and you will mostly see the caspase 3 activation. So this is our radiation oncology field. I am a basic radiation biology scientist, recently incorporated in the radiation oncology department, and a lot of work we have done in collaboration with Japan and Pakistan, and we have already started work with the on nanorods and on hyperthermia in our. So this is my email. If you want to have further queries regarding the physical modalities, I'm interested to answer that. And one request that I want to make for the Mastro, that please try to include a radiobiology session in your next year. If the leadership is there, I don't know, or you can pass my message, because in radiation oncology is limited if you are not covering hyperthermia, ultrasound, and other physical modalities that are actually FDA approved and can provide adjuvant to radiotherapy. Thank you so much.